Fine. So it's a great pleasure to have here today talking to us Paolo Perinotti, which is not only a person that a scientist for which I have a deep respect and a deep esteem, but also a friend, a very good friend, and we know each other since I think a quarter of a century right now, since we were both students at the University of Pavia. So Paolo is mostly interested in the foundations of quantum theory and physics in general, and has been behind some of these important works that came from the University of Pavia. I'm thinking now in particular about the series of works on the reconstruction of quantum theory from informational axioms, or the series of works about quantum circuit architecture and higher order quantum transformations that include the famous right now the quantum switch, which is this machine that is able to exchange the order of two channels. And so today Paolo will tell us something that is related with the causal structure of quantum theory. And in particular, he will tell us about differences on two notions that are typically equated. The notion I'm speaking about, the notion of no signaling, and the notion of absence of causal influence between two events. And he will frame this question in a very general way, which also goes beyond quantum theory, and so might be able to deal with extensions of quantum theory, perhaps. So I think that many people in the audience might be interested also in these potential extensions of quantum theory to deal with problems related with causality and signaling. Yes, I think that I can give the stage to Paolo. And for about questions, Paolo, do you prefer to have questions asked during your talk, or you prefer to keep questions for the end?
Well, I think that if someone has some interesting point during the talk, it's fine to receive it also in the meanwhile. I have no problem.
Okay, so I will keep an eye on the chat, and I will keep an eye. Yes, maybe I would ask the audience if there are people with questions to write one line in the chat, and I would interrupt Paolo in a good moment and ask the question. Okay, so the stage is yours, and yes, please.
Thank you. Thank you, Francesco, for the great presentation, and thanks to all the organizers. It's a great pleasure for me to have this opportunity. And as Francesco anticipated, my talk today will be about the notion of causal influence in a general scenario encompassing quantum and classical theory, but not only that one. So let me start with a summary. Oh, sorry. There was a problem. Okay, with a brief summary of the content of the talk. First of all, I will frame the problem of the relation between causal influence and signaling in this general framework of possible theories that encompasses quantum and classical theory, but goes beyond them and can encompass other maybe fancy theory, post-quantum theory. This is the framework we call the framework of operational probabilistic theories. These are theories that share with quantum and classical the basic structures. And by this, I mean the ability of describing the composition of systems to make a composite system out of subsystems, and composition of processes and events. So sequences of processes can be described in terms of the component processes, physical processes that are connected in a chain. And within this framework, one has the ability to describe a complicated process in terms of a network of elementary processes occurring. And as we will see, this gives rise to a very natural way of introducing causal cones. But the notion of causal cone that we introduce on these networks of events in general theory are very weak. So they only provide you an information like what events cannot affect other events. So the question I'm trying to face here is when the presence of a given evolution interaction between two systems allows the first one to affect the second one. And typically, the way in which this property of an evolution is referred to is signaling. And I will, on the other hand, focus on another related notion, which is the propagation of interventions. I will intuitively illustrate the difference between these two things with an example which is related to the picture that I have here. So a drop that falls on the surface of a pond with a circular wavefront that starts moving from the center. I will discuss the notions that I will introduce in the special cases of classical and quantum theory and use them to illustrate the main features of the two properties and also the difference between the two. And then I will show some interesting results about the relation between signaling and causal influence. And in the last part, I will focus on the conditions under which the two coincide. So we see that in quantum theory, actually signaling and causal influence are synonymous, but this is true because of a special feature of quantum theory that I will highlight and use as a hypothesis to prove that all the theories that share this special feature, which is no interaction without disturbance, have the property that in the theory, signaling and causal influence can be taken as synonym. But let me focus on the example I was mentioning here to start explaining a little bit better what I mean by signaling and propagation of intervention. So this is a typical situation we can think of to understand what we mean by causal influence. So we have the drop falling on the surface of the pond, and then the circular wavefront moving away from the center, and the wavefront moving makes two things. The first one is propagating an intervention. So we have the drop that falls in a very special point of the pond, but after a while, this intervention that occurred locally is spread along all the points reached by the wavefront in the time interval in question. And the other thing which is related to this propagation of interventions is the fact that the wavefront brings some information. So if you sit on the shore of the pond, if you sit on the shore of the pond and see the wavefront coming, this event witnesses the fact that something occurred at the center of the wavefront. So it brings you some information. It carries some information. So these are two things that I will try two aspects of a causal influence, which I will try to disentangle in my talk. So I will start with an introduction. I will make a crash course on operational probabilistic theories. I will try to illustrate all the basic facts that are needed to talk about the notions I discussed in a general way. So what is an operational probabilistic theory? It's made, first of all, by an operational language, which is a language that allows you to associate mathematical objects to physical processes. So for example, in quantum theory, we would have a quantum instrument that describes the most general conceivable physical process. The quantum instrument describes what happens in a quantum measurement. It's a collection of completely positive trace and increasing maps that sum to a channel. And the label by which you label the special quantum operation is identified with some classical information, which is the thing you read out on the pointer during the measurement. And conditionally on this classical information, what you know is that some process occurred. So some transformation occurred on the state of your system, which is represented by the quantum operation labeled by the special label corresponding to the outcome of the measurement. So in an operational language, you want to have something which generalizes the notion of a quantum instrument, plus some rule to compose instruments in parallel and in a sequence. So as you see in this picture, I drew a box in parallel with another one. You have to think of the information flow from left to right. So the input of of a test is the wire that comes on the left, and the output is the wire that goes out on the right. And as you see, I draw boxes in parallel and wires in parallel. These are these are the pictorial way of representing the parallel composition of systems. So two wires in parallel represent two component systems that are composed to make a composite one. And two boxes in parallel are just two independent tests run on the subsystems making a composite system. So I will use somehow this ambiguity, which is the box can represent either the full test or a single event within the test. So unless there is the need to specify things, I can leave the ambiguous notation there, because this means that the results hold both in the case of in case in which in the box I'm considering a test, and in the case where in the box I'm considering just one single element of the test, which is in the quantum case would be a quantum operation. And then we have another rule, which is the rule for composing tests in a sequence. And this is a very simple rule that comes in the operational language. So you have system types. Every system has its own type, like an electron, a photon, or maybe better, a mode of the electromagnetic field, a mode of the Dirac field. And one test can be composed in sequence with another one if the output system type of the first test coincides with the input system type of the second test. So for example, you can connect a photon source with a photodetector because the output system of the source is a photon or a mode of the electromagnetic field, and the input system type of the photodetector is again the same electromagnetic field mode. So we have a rule for composing systems in a sequence, and each connection like this makes another process of your theory. And then we have a rule which is much simpler for the parallel composition. Every two systems can be composed in parallel, and once you have a composite system made of two subsystems, you can run independent tests in this way. So every possible test from which has as an input system type A, and every other test which has as an input system C, can be run in parallel on the composite system AC. So they make one special kind of test that can be run on the composite system AC. And then, of course, among all these boxes with two wires at the input and two wires at the output, there are, of course, parallel composition of independent tests, but also interactions, also non-trivial tests that make the two systems interact. And these are the ones that would be most interesting to us. Take note of these special shapes that I use here and there, because I will come to them in a moment. So another thing which is very important in the operational language are the properties of the composition rules. In the first place, both parallel and sequential composition are associated. This is very simple. It means that if you consider, for example, a test on system A and a test on system B and a test on system C, you can think, first of all, as the composite test on system AB, made the parallel composition of the first two, and then take this big test in parallel with the test on system C, or you can start composing the test on system B and C, and then once you made the composite test, you compose it in parallel with the test on system A. And these two ways of composing the three tests together gives anyway the same result. So this is the associativity property. I will not go much into the detail on this, it's very intuitive. I will stress a bit more the fact that all the composition rules that I listed have a unit. So for example, for sequential composition, the unit is some test made by a single event, which is the identity event. So the identity test, which contains only one event, which is the identity event, is the test or the event that can be composed in a sequence with any box and leaves it unchanged. So if you have a box from system type A to system type B, you can take the identity test for system B, compose it after the yellow box and leave it unchanged. Or you can take the identity test on system A compose it before the yellow box and leave the yellow box unchanged. And also the parallel composition of systems as a unit, which is the trivial system. It's a system that can be composed in parallel with your system type A, both on the left and on the right, and we leave system A unchanged. To have a picture of what can be such trivial system, think of the quantum case. In quantum theory, the type of a system is associated with the dimension of its Hilbert space. And the trivial system would be a system whose Hilbert space is dimension 1. So of course, if you take the tensor product of a Hilbert space of dimension 1 with any other Hilbert space, the result that you have is that the other Hilbert space is unchanged. Its dimension is again equal. The dimension of a composite is equal to the dimension of the Hilbert space itself. So composing in parallel with the trivial system means adding essentially nothing to the system, adding some trivial information. But this special system plays an important role, as we will see in a moment. So we will often draw the identity event as or the identity test as a straight wire. And this will make things a bit simpler and intuitive. I will show you in the next slides. So a wire represents a system or nothing occurring on the system, the identity test running on that system. Now, let's consider tests from the trivial system type to some other type system B. So the pictures that I drew in the previous slide, which have a curved side, are actually a shorthand to represent tests from the trivial system to system B. These are preparations, right? So you have some trivial information and you run a process that transforms it into some state of the system B. So this is a state preparation. And on the other hand, you have tests with input type A and output type trivial. So these kind of tests are measurements. So you can think of them as demolitive measurements, or simply measurements where you just run the test and then discard the system. You forget about what happens to the system afterwards. So the trivial system will be very important in a while, but let me use here the fact that we have an identity test, because this allows us to introduce the notion of a reversible event. And this will be very important in the discussion of causal influence. So a reversible event is an event like the green one that I draw here, such that there exists another one, the yellow one, which can be composed after the green one or before the green one. And in both cases, the sequential composition gives you the identity test on the input system type. So in this case, yellow after green is the identity on system A, whereas green after yellow is identity on system B. So reversible events are essentially like unitary transformations in quantum theory, and are isomorphism of system types.
Paolo,
And yes,
there is a question on the chat from Masahiro Hotta. He asks, do you assume locality of the theory when you introduce the associativity and the existence of the unit operation?
Okay, no, there's no assumption about locality. Locality can be a feature of some special reversible evolutions, a special interaction involving many systems. So if you have many systems and you have a reversible evolution of those systems, it may act non-trivially only on a few of them, and then we say that it acts locally, but it can also involve a very delocalized evolution. I think the question was referred to this point. Otherwise, there is some other notion related to locality, which is the possibility of testing the states of the theory locally, which is local discriminability. But in any of these two cases, I'm not assuming anything about the properties of the evolutions and the measurements. So you can, in principle, have highly non-local processes, highly non-local encoding of information in the theory. I hope this answers the question. Okay. So a very special case, an important case of a reversible event is the swap. Actually, I would call it swap for the case of symmetric theories, which are theories where the swap is involutive. It coincides with its inverse, like in this case. The swap will be drawn schematically in this way and does a very intuitive thing, which is to allow two boxes to be swapped, exactly as the name says. So this is the defining property of the swap reversible operation. And as you see, you can think of the swap as the possibility of dragging the boxes along wires. So you see, if you drag the blue box on the bottom on this side and the red box on the top, you get the picture on the right-hand side. And so the possibility of dragging boxes is also connected to the fact that we draw the identity as a wire. And I will discuss more in detail this observation here. So the most important rule that comes with the parallel and sequential composition is this one. So suppose that you have this disposition of 4 boxes, and you take, first of all, the parallel composition of these two and the parallel composition of those two, and then you make these two big processes for the composite systems, and finally you compose them in a sequence. Then what you get is the same transformation that you would get if instead you considered first the sequential composition of these two boxes, then the sequential composition of these two boxes, and then finally the parallel composition of the two big boxes that you obtained. So in formula, this property is the following one. So you can take first the parallel composition of A and B, then the parallel composition of, first C and D, then A and B, and then compose them in a sequence. And this is the same as A after C, this one, in parallel with B after D. So if you consider the way in which we draw identity, the above property allows us to draw this very intuitive diagram, which is again an instance of the fact that you can drag boxes along wires as long as they don't hit another box. And this is a way of saying one important thing. So local processes on component system must commute. So it's irrelevant whether you consider that the yellow box happens after the red one or before the red one. That's because they act locally. They don't represent interactions of the two subsystems. So now we have a descriptive language that allows us to set the basic rules. One thing that I didn't mention is that actually you can generalize this feature of the swap to theories where the swap is not involutive, so braided theories. This would be a complication that we are not going to consider in this case, but I just wanted to mention the possibility of including a braiding instead of a swap, a non-trivial braiding in the theory. So, okay. So now we have a descriptive language that allows us to describe the composition of processes into complicated composite processes. So networks of processes composing parallel and in sequence. But this is just a descriptive language. The predictive power of the theory comes from the probabilistic structure. So once we have a network of processes, we also want to predict what is the probability of occurrence of the single events in the big test that we prepared. And this possibility comes from the requirement that we impose on systems, on tests of the trivial system. It's a very easy rule. Every test of the trivial system is a probability distribution for its events. But it has an important consequence. For example, consider a test like this one, which is made by a preparation test followed by an observation test. So if you compose them together, the global input will be trivial, the global output will be trivial. So this represents joint probability distributions for all the outcomes, I and J. So it's a joint probability distribution for I and J. So as you see, this observation can be made also for more complicated networks, as long as they are closed by a preparation at the input at the very beginning and an observation test at the very end. In this situation, you can assess the probability of every single event in the network. So Now look at this situation. Suppose that you consider aj as a variable and rho I as a fixed element of the set of states of your system. Then, as you see, this rho I is a function that accepts an effect. So an effect is an element of an observation test. An effect is an input, so this is the variable, and produces a real number. So you can think of states as functionals on effects and vice versa. Vice versa, you fix aj and you change rho I. This one becomes the variable at this time. So the effect aj is a functional on states rho I. So you can, it's very natural in this situation to embed the set of states of the theory and the set of effects of the theory into reciprocally dual real vector spaces, which are the spaces that denote by this symbol, the space of states of your system and the space of effects of your system. So you can think of states and effects as vectors. And what about transformation then? Transformations induce linear maps. This is easy to prove. But one thing that is non-trivial is that actually they induce families of linear maps. And what I mean by this is that if you consider a transformation T composed in parallel with the identity transformation, of course, this is a special transformation of your theory. And then if you take a basis of vectors in your space of states, labeled by the symbol I, what you get is an output state, which is a linear combination of a basis of elements in your vector space of output states. And the linear combination has coefficients which make a matrix. And this matrix represents the linear transformation corresponding to this special transformation. But you see, if you change the system on which you act trivially, you might have a different matrix there. And it's not trivial that this matrix is simply related to the matrix that you get if you act only on system A. So don't be fooled by the fact that I use this symbol here. Parallel composition does coincide with the tensor product rule for matrices only in some special theories, but in general, this is not the case. So this parallel composition does not correspond to a tensor product representation for this linear map in general. So if you want to specify a transformation, you have to give all these matrices for every possible choice of system C. And that's why I'm talking about the family of linear maps. And then in special cases, it might be that there's a preferred element of this family that allows you to specify all the other ones via some simple rule, like a tensor product with identity matrix. To illustrate an example of the necessity of this family of maps, consider a real quantum theory where the Hilbert spaces were considering a real Hilbert spaces. So in this case, the density matrices are symmetric, which means that the transposition acts on density matrices as the identity. So if you look at the action of transposition locally on your system A, you will not notice a difference with the identity. But it happens that, for example, this is an element of the state space of your composite system AC. And then if you act locally by transposition, you will get this extra minus sign. So transposition is different from the identity, but in real quantum theory, you will need to check what happens on a composite system to realize the difference. So that's why the matrix representing the transposition in this composite transformation is not simply the tensor product of the matrix representing transposition on state rho tensorized with the identity matrix. So that's why we need, in general, families of linear maps to specify a single transformation. And since we want to talk about causal influence, a very important and natural assumption to make is that the theory is causal. It doesn't allow for non-causal effects. So the way in which I define causality is the following. So the definition is that you're allowed to do in your theory any conditioning you want. And what I mean by this, so suppose that you have run some tests on your input system, you have now an output system, and you have an information, which is the outcome of the measurement, I. So you can use this piece of information to decide what to do next on your output. So you choose another test as J, which is labeled by I. I denotes your choice of a subsequent test. And if you can do that in any conceivable way, so you can choose any collection here conditioned by this label I, and this new test is an allowed test of your theory, then you have causality. And this implies some important consequences. For example, a non-trivial consequence is that if you have this property of causality, if you can do conditioning in any conceivable way, then you cannot have backward signaling. So suppose that you have a scheme like this, like a preparation test followed by a measurement test. In general, if you marginalize on the output, you get some probability distribution of the elements of the input, which depend on the choice of measurement that you make. Of course, they do not depend on the outcome, but they do depend on the choice of measurement. Well, the causality property implies that the dependence is washed away. And so there's no way of choosing the measurement here to change the probability distribution of the input, which means there's no way of signaling backward in time. And equivalently, this means that there's a unique deterministic effect in your theory. So now consider a circuit of processes like this one in operational probabilistic theory. And consider, for example, these two systems, and you ask what are the events that can affect the state of these two systems. So the causality property tells you that all the events within this past light cone, causal cone, sorry, can affect the state of your system on these two wires, but all the other events here cannot affect this state. And vice versa, the state of the system of this wire, for example, can affect the probability of these events in the future causal cone, but not that of events outside this future causal cone. This is a very weak notion of causality, because it might be that if you know something more about the structure of boxes like this one, you can maybe change the structure of your cone. So for example, if this box is factorized, is a parallel composition of two boxes, and you look at the state of this wire, then its past causal cone actually is narrower. It's of this shape, okay? So this is an extreme case of simplification of the cone of causal influence, but the kind of question I would like to address now is what are the conditions under which the presence of a box actually allows for causal influence between two different wires in this way, and under what other conditions instead this is forbidden. So we want to make this causal order relation sharper. So the simple causal relation order introduced by the property of causality tells you what influences cannot be there. But now the question is, what are the actual influences that are there within the circuit? So we want to characterize the property of a box like this one to say whether it allows for causal influence from one input to one output and vice versa. So now now it's time to introduce the main properties of the talk, which are the signaling and causal influence notions. And let's start from signaling. So the question now is, when is it possible to send signals? Or actually, the question is negative. When is it impossible to send signals from a system to another? So a typical scenario where you can imagine to send signals is the following. You have some agent controlling a lighthouse, and it would like to communicate to a vessel so it can switch the light on. But if there's an island in the middle like this, it's clear, very intuitive, that there's no signaling from the lighthouse to the vessel. So whatever the agent does, the vessel does its evolution independently of what happens on the other side. And this can be imagined in this other way. So now suppose that after this evolution, we erase this part of the picture. Okay, then what we get is the same that we would have gotten if we erase this part of the picture from the very beginning. So you see, no light comes from the dark side of the picture. So if there was light from the dark side of the picture, then this information wouldn't be sufficient to determine what happens in the full evolution. You would need to remove the dark part of the picture and see also the agent acting. But since there's the island in the middle, then we can erase this part of the picture and just look at the vessel. So the full dynamic of the vessel is given by its input state and is uncorrelated with the state of the lighthouse. So let's make this notion more formal.
Paolo, before you continue, there was a question in the chat. Maybe Arthur can ask directly if you like.
Yeah, so before you, maybe 3 slides ago, you gave a definition
Yeah.
of causality in terms of conditioning. And then on the next slide, you drew an example of a circuit. But I didn't see that definition appearing anywhere when you talked about the causal past. It seemed like you can make sense of that definition without the previous slide. So am I missing something, or?
Okay, the point is that you have no backward signaling, right? As a consequence of causality. So these pictures, this picture means nothing on the causal level if you had backward signaling, because, for example, this event might anyway affect anything with this cone, because you can move the influences backward along the wires, right?
I think I see. It's hard for me to see exactly what it means to condition in terms of this. Like, are you talking about like a string diagram that moves back and then
no? I'm using just a consequence of conditioning, which is the impossibility of sending information backward along wires. Okay.
I see. So with that definition, then you can justify defining this as the causal past.
Yes, exactly.
I see. Okay, great. Thank you.
It's a weak notion that tells you what if events cannot affect other events. But the question now is what events do actually intervene in the determination of other events. Did I make the point clear now?
Excellent. Yes, thank you.
Thank you. So just okay, sorry. Okay, so let's make the notion of non-signaling more formal now. What I claim is that this channel C with input AC and BD cannot allow for signaling from A to D, so it's non-signaling from A to D. If this happens, if when you discard system B, which is anything but D, it's like discarding A from the very beginning and doing an independent channel from C to D. So why is that non-signaling? Because suppose that we tweak somehow the state of system A. You do it because your purpose is to send information to system D. However, this property tells you that what you get is anyway this thing, because the pink channel preserves the deterministic event effect here, which is unique because of causality. And then whatever state you plug at the input, as you notice here, what you get on system D is determined by this very diagram, which means that everything that matters is the marginal state of system C, independently of whether you acted with the pink box on system A or not. So what D will get is completely independent of any possible information which is encoded on system A. So that's why this property is called no signaling. In the quantum case, it's translated by a very nice algebraic condition on the Choi operator of the channel C, which is its partial trace on the output system B must be proportional to the identity on system A, which is a unique deterministic effect of system A, and so the Choi of the channel from system C to system D. So now, talking about propagation of interventions, the other notion that I would like to discuss. Think of a stone falling on the surface of a pond, and now you see a wavefront moving from the center of the where stone fell on the surface of the pond. So you have this pattern of waves on the surface. Now let's remove the stone from the picture and concentrate on this pattern. And the question is, suppose that instead of the stone, we started with an initial condition. We let the pond evolve with its normal dynamics, which means it arrives at this point unchanged, unperturbed. And we want now to reproduce this pattern without the stone, acting locally on the points of the pond. So for example, we need to act non-trivially on these 3 yellow spots, because there the level of the water is raised or decreased, depending on whether you're on a top or on a valley of the wavefront. But if you consider, for example, the green point there, where there you have to do nothing in order to reproduce this pattern. So the evolution of the pond propagated the intervention at the center of the wavefront on these 3 yellow points, but not on the green point. So that's the thing that we would like to formalize now, propagation of interventions. And in the first place, it's possible to do this only for reversible transformations. That's because here's a raw definition. It's not the precise definition. We'll come back to this in a while, but to give you a raw picture, a raw idea of the definition, I want to give, I see to this simplified scenario where you have a yellow evolution, like the evolution of the surface of the pond. This is the reversible transformation we would like to talk about, whose causal structures we would like to talk about. Here's an intervention on system A, and then we reverse transformation U, which its inverse on the left-hand side. What we get generally is a transformation that involves both system C and D. But we say that there's no causal influence from A to D if whatever intervention I make on system A, this transformation is factorized in this way. So identity on system D. So there's no intervention I can make on A to avoid the fact that here I have identity. So now the precise idea. By the way, the symbol that I will use for no causal influence is this straight arrow, whereas for signaling I had a curly arrow. So this is the definition of the raw definition of no causal influence. So in this case, we can say that A has no causal influence on D through the evolution given by U. So now the precise definition. What's the difference? Here I'm just considering one thing more, which is the possibility of having an arbitrary ancillary system here and the intervention involving also the ancillary system. Okay, but the definition is exactly the same spirit that I illustrated before. So this is important in theories where you don't have local tomography or tomographic locality, or as I prefer to say, local discriminability. But this is a technical issue. It's not so relevant. So let me rather discuss the reason why this definition actually translates the notion that I discussed before. Because you can rewrite the condition of no causal influence from A to D in this way by just inverting the green box on both sides. So you see here, the green box disappeared, and here it's the identity is substituted by U. So now you see, I have an intervention on system A, plus maybe an ancillary system E, then the free evolution of the system. So now I'm trying to mimic the effect of this thing by just letting the system evolve freely here and reproducing the effect by acting afterwards. So if I don't need to touch system D, like in the green spot on the surface of the pond, then I will say that the intervention at A was not propagated to system D. And if this happens for any conceivable information, this means that it's the evolution U that does not allow for causal influence from A to D. So now we have the definitions, and let's discuss some results. So the most striking thing is that signaling is a sufficient condition for causal influence. So now I defined no signaling and no causal influence, but of course I can define signaling and causal influence by negation. So we have signaling if there's no signaling, and we have causal influence if the conditions for causal influence fail. And the interesting thing is that if you have signaling from one system to another, then this is a signature of causal influence. So it's a sufficient condition for causal influence, but the converse is not true. So you can have causal influence even in the absence of signaling. Before showing this point, let's start with a necessary and sufficient condition for no causal influence. And in order to do this, I will involve the swap test. It's a very important transformation in this respect. So let me define this transformation T, which is connected to the reversible evolution U, which is the one that you obtain when you conjugate the swap on the input system A with an ancillary system, which I call A1, with the reversible evolution U. So now the necessary and sufficient condition for no causal influence is that this box is actually factorized in this way. So you have a box on the ancillary system and A prime, and I tensorize with identity on B prime. Of course, it's clear that this is a necessary condition because this is just an instance of the general definition where I plugged this very special intervention on system A, which is the swap. But interestingly, this is also sufficient. So if this happens for the swap, then it will happen for any other intervention. The proof is rather simple, but I will not spend time on the proof. Rather, I would like to show you this consequence of the necessary condition, which I call the COM structure. So we can rewrite the necessary and sufficient condition in this way. And this means that I inverted U on both sides. And now, if you prepare a state of system A and discard it on both sides, so here you see I have the number 1, factor 1, and what remains on the left-hand side is just U. And on the other side, I have this fancy structure, which is the one I call the COM structure. So the result is this one. If I have no causal influence from A to B prime actually, then this reversible evolution multi structure can be thought of these special structures, like a memory channel, first on from system B to B prime with a possible ancillary system E, the memory, and then a second process that involves A and D and produces system A prime. So now it's easy to prove that then it's necessary to have no signaling, because what you do now is discard system A prime. And if this is the case, you see that this process just brings the deterministic effect on A and D. So you remain with the discard of system A and the channel from B to B prime. So here I forgot to put the label. So this is exactly the condition for no signaling. So if you have no causal influence, then you have no signaling. So we have this chain of conditions. If the evolution U doesn't allow for causal influence from A to B prime, then the evolution U must be decomposed in this way. And then as a consequence of this, you have no signaling. So the question now is, what about these arrows? Which of them can be reversed? And to phrase this question, we start with an example, which is classical theory. So in classical theory, one can prove that no signaling implies the COM structure, okay? Which means that the second arrow can be reversed. So these two conditions become equivalent. So the question now regards just the first arrow. And to tackle this question, consider the classical C0. Okay, the classical C0 is the reversible evolution that acts in this way. You have two bits at the input, A and B, and they are evolved into A and A sum modulo 2B. So now if you discard B prime on both sides, it's clear that on the right-hand side, this state will disappear and you remain with A. So we have this picture. And since this is true for every possible input A and B, this means that we have this equality. So if we discard B prime, the target, after the action of the classical C0, we have identity from system A to A prime and the start of system B, which means that the C0 is non-signaling from the target to the control. But if you do the calculations for the necessary and sufficient condition for a causal influence, you see that it's violated. And this means that you have causal influence from the target to the control. What is this causal influence? Well, if you think of the C0, you can use it to copy the control bit onto the target bit. So you are creating a correlation of the input state of system A with system B. And so the causal influence is not in the change of the local state, but in the change of its correlations with the outside world. And so in classical theory, the chain of condition becomes this one. So you have a counterexample for this direction, which is the C0, and you have the equivalence of these other two conditions, so COM structure and signaling. What about quantum theory? So also in quantum theory, you can prove that no signaling implies a COM structure. And also in quantum theory, then we have this reduction of the diagram. But what about the first arrow in quantum theory? Well, in quantum theory, you can prove this fact. So it can be proved using the mathematics of the Krauss decomposition of completely positive maps. So if you have a quantum instrument such that if you cross-grain it completely to a channel and you discard the output system C, then you have discard of system A tensor identity. Then it means that every single quantum operation in the test must be factorized in this way. And this is a rather simple property to prove. It can be also proven starting from purification without assuming the full machinery of the mathematics of Hilbert spaces. And this means that the same result holds in fermionic theory, real quantum theory, and theories with purification plus some little extra gadget. We call this property no interaction without disturbance. Why? Because if you have an interaction like this, a channel like this, and you discard the output, what remains on this side is the identity. So this, we can say somehow that this interaction does not disturb system B. Then it's actually not an interaction because it's factorized, and on system B you just have the identity. So no interaction without disturbance. This is the property that I would like to assume now as an hypothesis. So if you have no interaction without disturbance, what you can prove is that actually no signaling implies no causal influence. So in theories where you have no interaction without disturbance, the diagram of conditions collapses into a unique condition. So no signaling coincides with no causal influence. So no interaction without disturbance is the hypothesis under which the two notions of no signaling and no causal influence coincide. If you don't have this property, then there might be a difference, and causal influence is somehow stronger than signaling. What about theories where you have interactions without disturbance? So what you can prove in this case is that if you have an evolution like this, where you discard system A and you have identity on system B prime, and plus you suppose that there's no causal influence from A to B prime, then what you can prove is that you have this factorization. So if you have an interaction without disturbance, this means that this factorization fades, and then the hypothesis must fall is that there's no causal influence. This means that in this case, this evolution is no signaling from A to B prime, but it bears causal influence from A to B prime. So if the special interaction without disturbance is reversible, you can always falsify the implication backwards in this way. So now let's come to some open questions which regard this structure, this hierarchy of conditions. So the interesting thing is that we prove that there's no, there's a counterexample in this direction, but in general, we know nothing about this arrow. All the theories that are considered have the feature that no signaling and the COM structure coincide. So it would be interesting to understand whether there's a theory where the two things are different.
Oh, there was a question, Paolo. Sorry.
Sure.
There is a question in the chat. Is this difference between classical theory and quantum theory related to the existence of the coherence?
Well, I'm not sure about the answer to this question. What I can tell you is that think of the C naught. In quantum theory, so if you quantize, let me use this word, it's the C naught, then it immediately reveals a kickback of the target on the control. So the quantization of the gate shows you the causal influence that was hidden in classical theory. So I think that this is related to the fact that in quantum theory you have some extra information which is about phases, and maybe on the long run it will be related to the coherence, but I'm not sure how to answer this question right now. I'm sorry about that. So in the last part, I would like just to give you some motivation. Usually one gives the motivation in the beginning, but now I imagine that someone could ask, so that's a talk within a series on extreme universe, so why should I bother about this notion? Well, causal influence is is basic in the physics of the universe because it's related to every geometric picture of space-time. What I claim is that space-time is the geometry of space-time. In the end of the day, is just a shorthand, a map for the structure of causal influences between events in the universe. And the project I'm working on is to model the evolution of physical systems, the elementary macroscopic evolution of physical systems in terms of quantum cellular automata. So actually, the notion of causal influence comes from the definition of a neighborhood of a cell in a quantum cellular automata. Because in that case, you're considering a grid of Hilbert spaces, which are the cells. Each one is associated with the local algebra transformations. And then a cellular automaton is a unity revolution on this big Hilbert space. And we define the neighborhood of a cell x0 if, when you conjugate the local algebra A x0, what you get is a subalgebra of the blue region in this way. So I have the local box, I let the evolution of the cellular automaton act for one step, and then the local algebra is spread in a neighborhood. Okay, so don't be deceived by the picture that I use. It's not that, you should think that it's not the neighborhood that dictates the evolution, but rather the other way around. So you have a unity revolution, and then you see how the cells are moved to other cells, and then you think of the cells in the neighborhood as close to the initial cell. So the evolution dictates a geometry on the array of systems making up a cellular automaton. So essentially, we say that there's a causal influence from x0 to any other cell y, which is in the neighborhood of x0. So in this way, you can construct a graph of causal connections on the array of the cells making up the cellular automaton. And there's a way of proving that this defines essentially a unique smooth geometry on some manifold in which you can embed the grid of the cellular automaton. And interestingly, we also derived some dynamical laws like Weil equation by just requiring some very simple condition on the cellular automaton. So looking at the simplest quantum cellular automaton in fermionic fields, you end up necessarily with the dynamics of a relativistic quantum field. So the remarkable thing is that all the geometry of this graph, which ends up in the geometry of space-time, which is the playground for these differential equations, are just causal influences. So in the end of the day, they boil down to the relation of causal influence that I defined in my talk. So one very fancy observation that I like to do as a comment to the results that I showed you is that in classical theory, the principle of action and reaction is actually an accidental consequence of the translation invariance of physical laws. But it's completely conceivable a classical universe where this principle fails, because you saw that in the case of the C0, you can have an action in one direction without seeing its consequent reaction. And on the other hand, in a quantum universe, there's no interaction without disturbance, so it's much more natural to have the third principle in a quantum universe than in a classical universe. So with this observation, I concluded, and that's just a summary of the things that I discussed. I would like now to thank you and leave room for possible questions.
Thank you very much, Paolo, for your very interesting presentation and also thought-provoking comments. Do we have any questions from the audience?
Can I ask a question?
Oh, yes, please.
Oh, thank you very much for very nice talk. And now I have a question. During your talk, you didn't mention about the relativistic causality, for example, special relativity and the general relativity. I'd like to know the relationship between the causal influence of your talk and the ordinary relativistic causality. Could you?
Yes, sure. There is actually a precise link, which is given by this picture here. So when we have a network of events in an operational probabilistic theory, we can arrange the processes in subsequent steps, and the number of the steps will be a logical time. And we can arrange the wires in parallel in this way, so we have a logical space. And in this logical space-time, which plays the role of the geometric space-time of special relativity, the cones of causal influence substitute the light cones. So the notion of causal influence plus the knowledge of the processes in your evolution automatically give rise to a Minkowski structure, a generalization of Minkowski structure in a network of processes, of physical processes like this one. So I would say that in causal theories, the Minkowskian structure is intrinsic in any process.
Thank you.
Thank you for the question. Indeed, if this network of processes were homogeneous, then the light cones would be perfectly regular. So it would be really cones like the ones we are used to think in special relativity.
Oh, thank you very much. Another question. I have another question. If you include closed time-like curves into your theory, so how about the modification of your conclusion?
Okay, in causal theory, it's not possible to include closed time-like curves safely. You need to change something in the framework. So either you remove the causality condition or closed time-like curves are excluded. If you want to include closed time-like curves, you must consider non-causal theories. Otherwise, you should think of closed time-like curve as probabilistic events, something which occurs with some probability. Like you can think of the teleportation scheme for a qubit, right? So if you do teleportation, quantum teleportation, you need to read the outcome of the Bell measurement in order to correct for the unitary in one direction. But one time every 4, you just have the right outcome and you don't need to do anything. So if you stretch the teleportation in time, you can think of the state measured at the end of the process as being teleported backward in time. So this is a closed time-like curve, but it happens with probability 1 over the dimension of the square dimension of the Hilbert space. So this nonlinearity, this renormalization brings nonlinearities if you want to consider deterministic closed time-like curves, but it can be done in this way. Otherwise, you have to consider non-causal theories.
Thank you very much.
I have a question. I think your framework is very general, and I'm wondering, do you assume anything about the dimension of the vector space? For example, state space and effect space. Do you need to assume it's finite dimension or infinite dimension is okay?
Okay, I don't need to assume that it's finite dimensional, but so you can include safely infinite dimensional vector spaces in the picture, but you have to take care because some results might fail there. For example, the duality, the perfect isomorphism between the state space and the effect space becomes a little trickier there, because every time you take a dual for the infinite dimensional case, you enlarge the space. So there are some little technical details that have to be taken into account, but in general, most of the results hold also for infinite dimensional systems,
including your conclusion today, like causal influence and signal.
Yes, actually, I studied most of these in the framework of cellular automata in operational probabilistic theories. So I wrote a paper on the generalization of the concept of cellular automaton to any conceivable operational probabilistic theory. And in that case, what I did was to construct infinite dimensional systems, even though, okay, the construction there was starting from finite dimensional local systems, composing them, infinitely many of them, and getting infinite dimensional systems. But in this case, anyway, I proved the results about causal influence. I used them to define the neighborhood of a cellular automaton in the general framework of operational probabilistic theories. So the results that I showed hold also for infinite dimensional systems.
I see. Thank you very much. And one more question. So maybe this is too naive, but in this slide, the space dimension, actually time as well, is kind of discrete. And I'm just wondering what happens, for example, in the field theory, everything is continuous, right?
Yes.
And if everything is continuous, maybe, some part it would be a little bit tricky, I guess. And
okay.
you make a comment
Thank
on
you. Yes, thank you. It's a beautiful question indeed, because, okay, I was mentioning here that the picture that I like is that instead of starting from the geometry and then deciding what is the neighborhood, it's the dynamics of the system that tells you what is the neighborhood, and then the geometry of the system. This can be done exactly in the discrete case. If you have a continuous case, then in order to define the evolution, you need, in the first place, to have a topology. So in order to define the neighborhood of the evolution, you have to put a topology from the very beginning. So it's not true anymore that you only have the evolution giving you the geometry. You need some geometric element before defining the neighborhood. And you cannot do this construction anymore. So things are trickier in the continuous case. But the point is that it may be that the continuum is just an idealization, like a limiting case where you have, for example, in this case, consider a wave packet. So consider states which are wave packets whose Fourier transform is peaked in some very small wave vector, which means the wavelengths involved in your state are not able to resolve the granular structure of this space. Then you can easily approximate your evolution as a continuous evolution by a differential equation and the propagation of a plane wave in a flat space, things like that. That's actually what we did when we reconstructed Wild's equation. And then in this very same spacetime, you can have some new effects given by very high energy processes that are able to resolve the discrete structure. So I like to stick to the idea that spacetime might be discrete in its very microscopic structure, just on a scale we are not able to reach in our present day technology.
I think that is the case in quantum gravity, I guess, although I'm not an expert.
In some way, yeah, some approaches in quantum gravity do something similar.
Okay, great. Yeah, thank you very much. Nice talk.
Thank you.
Any other questions? Okay. I don't see anything in the chat. I don't see any raised hands among the participants. So I would like to conclude here. But before, I would like to thank Paolo again for this beautiful talk and for the discussion that followed it.
Thank you.